In this problem, we're being encouraged to use horizontal strips to find the area. We talked about this in class last week, but up till now, we've been working with integrals in terms of x, which means the strips go up and down like this, vertically. If we try that here, though, as you move across the region, when the strip is over here, the top curve is going to be the line, and the bottom curve is the parabola, which is okay. But when you move your strip over to this part of the region, and it would go up to here then, now the top part of the curve is the parabola, and the bottom part of the curve is the parabola also. And so you could do it like this, but you'd need to write two different integrals, and it's much easier to do it the other way. And by other way, I mean situate the approximating rectangles so that they are arranged horizontally, which is what they mean here when they say use horizontal strips to find the area. So this means that we're going to write this as an integral in y. So we need to solve both of these equations for x and find the points where they meet and set up the integral. And so here I have both of those functions graphed in Desmos, and we need to find, among other things, we need to find the places where they cross. So I think you can just click on these points and get those values. And we want the y parts of each of these points. To find these by hand, let me get that screen up. So to find the points of intersection by hand, here are our two equations. Since we're treating this as an integral in y, we want to solve both of the equations for x. The second one already is. This one will have x is equal to 1 divided by, and I think this has come up before in this class. Like, you shouldn't do this. You should choose between a fractional representation or a decimal one. 2.75 is 11/8. So 1 over 2.75 is 8/11. So we have 7.5y, 7.5 minus y squared is equal to, this is 8/11 times y. So that's pretty ugly, but it does come out to a quadratic that we can solve using the quadratic equation. You can also graph this on your calculator and find the points where, exchanging the y's for x's, where this thing hits the x-axis. You have a lot of tools to be able to solve this equation. And so now that we've found the points of intersection, we can write our integral. The area trapped between those two curves, we want the lower value of y, negative 2.926, up to the upper value of y, 2.563. And then for the integrand, we want to take the rightmost curve and subtract the leftmost curve. So here we want the parabola minus the line. And we can use the power rule to evaluate this. And I'll leave it to you to plug those ugly numbers in and get the final answer here. To enter the answers into MOM, the lower bound for the integral is our negative 2.563. Our upper bound is, oops, I did it wrong. Lower bound is negative 2.926, and the upper bound is positive 2.563. The function that we're integrating is 7.5 minus y squared minus 8/11 times y. And they've already entered the dy here. And then I evaluated the integral, and I got 27.567. Which certainly seems in the ballpark. If you look at this picture here, this is 2 units between here and here. So every large block here is 4 square units. And so there's about 1, 2, 3, 4, 5, 6 of them, sort of, more or less, which would correspond to 24 for the value of the integral, again, because we're trying to compute the area trapped between those two curves. So this answer certainly seems reasonable.